Thank you so much. And thank you very much to the organisers of this session for inviting me to come and speak today. I had to think whether the minerals I study are exotic or ubiquitous, and I'm not quite sure whether they're exactly exotic. They're certainly not ubiquitous. But anyway, what I want to talk to you today about is some of these kind of rare uranium, thorium containing minerals and how we've been using them as templates for radioactive waste disposal matrices. So the context that I'll start with, you see this big plutonium symbol in the background. There's no plutonium in my talk, but there is a lot of uranium and thorium. But the context for the work is trying to understand what to do with the inventory of civil separated plutonium that we have in the UK. So we have the largest inventory of plutonium in the world. We're not good at winning a lot of things in the UK, but we're winning on this. We have the largest inventory of this material that comes from nuclear fuel reprocessing operations. It's not necessarily something that you want to be winning at, I don't think. But the government strategy is to put this material, what they call beyond reach. This is the policy. And there's two ways in which this can be done. The first one is fabrication of a mixed oxide fuel for burning in nuclear reactors. So this is a mixed uranium-plutonium oxide fuel. The problem with this at the moment is that there are no nuclear operators in the UK who want to do this. There's also no facility to fabricate these fuel pellets. So what we're left with is a rather large amount of material that's stored in, you can see on the front cover of this magazine, this is the exact store where we keep plutonium in the UK. And this material needs management, it needs processing, it needs to be looked after, and it's costing an awful lot of money just sitting there. There is a portion of this inventory that's unsuitable for use in a mixed oxide fuel. And so this is material that was placed in PVC bags, and obviously plutonium undergoes alpha decay, this degrades the PVC, and then all of a sudden the plutonium becomes contaminated with chlorine and you can't reuse it as a MOX fuel. So part of the inventory already is not suitable for this beyond reach strategy of turning into a fuel. So we have to think of another option. And this is immobilisation, and this is where the minerals come in. It might be possible that if we have a change in the policy in the UK, which may happen in the next few years, that we think about immobilising the entire inventory into a stable material, which I'll talk about just now. Okay, so some of the issues are that plutonium is obviously radioactive. It's going to emit alpha radiation for a long time, and its daughters will as well, so uranium-235. And during this time, it will obviously be hazardous to the biosphere, future populations, and so on. So what the current proposal is, if we were to dispose of this inventory in an immobilised matrix, it would be in a geological disposal facility. This is the UK concept at the current time. So you access the facility from the land, and then the disposal part is actually out here under the sea. And we would immobilise this plutonium material in a ceramic host matrix, it's a mineral, to create a passively safe, durable and radiation-tolerant waste form. And so natural uranium and thorium containing minerals provide really good templates for the development of these ceramic materials. And I mean, if you're interested, this is the current status of where we are with disposal in the UK at the moment. It's a voluntary community process, and we have 3 communities in discussion with the UK government. 2 of them are just over here. This third one kind of dropped out recently, so 2 over here and 1 over here. There are some non-intrusive geological surveys underway, and we're expecting a decision on where the intrusive investigations, boreholes and so on, will be made in the next few years. So things are moving forward. Okay, so back to the minerals. When we sort of start thinking about what kind of minerals might be suitable as a host immobilisation matrix of plutonium, we kind of wind the clock back to Ted Ringwood and the work that he did in the late 70s and early 80s on a material called synrock. So this is a synthetic rock, a series, a combination of titanate minerals that was developed for the immobilisation of fission products from spent fuel reprocessing. This is just one extract from one of the papers that I quite like. You can see before and after images here of the synrock, the titanate mineral assemblage, and borosilicate glass, which is what is used for immobilising fission products. And then he subjected them to some rather harsh conditions. I have to say that 4 days at 300 degrees C is not representative of a geological disposal facility where the waste will be more likely 40 degrees C. But what you can see really clearly is that the glass doesn't behave very well. You know, it corrodes quite significantly and it fractures and falls to pieces. Whereas the synrock somehow looks shinier before than it did afterwards. I think that's just an artifact, but you can see it's still intact. So synrock is as I said, an assemblage of titanate minerals. You can see them here. So different minerals, so hollandite, pyrochlore, and so on. And all of these can accommodate different types of radionuclide species. So for example, on the hollandite, you could take cesium or rubidium onto the barium site. Pyrochlore and zirconolite are very chemically flexible. You can take in rare earth fission products, actinides, and so on. And the perovskite, you can even include some strontium on the calcium site. Rutile doesn't really accept anything, but it's there as a buffer phase. So there's a wide range of different minerals that we could start to target for plutonium immobilization. And the ones with actinides here, so pyrochlore, zirconolite, perovskite, these are the ones that you might want to target to put your plutonium on. Perovskite less so because it's not quite as durable as the others. So pyrochlore and zirconolite are two serious contenders that have been investigated in the past for this particular role. And obviously in nature, we find them containing uranium and thorium. So we know that these minerals are geologically stable. We have lots of evidence from natural minerals. As I say, these have been studied before. This is not a new concept. We know that they're able to retain a significant actinide inventory over durations of billions of years. And actually, for geological disposal of radioactive waste, we only really need 1 million. That's where the most hazardous time of radioactive decay will have passed. We know they have a high resistance to self-irradiation damage. So there are samples that are, very old that are still not completely metamixed. They still have some crystallinity. Excellent aqueous durability over these long time periods, so subject to hydrothermal alteration, to meteoric water alteration, and so on. So very durable. They retain their actinide inventory for a large part. And the actinides are in a tetravalent oxidation state, and that's important. I just showed the Pourbaix diagram here for UO2. And what you can see is where we have uranium 4+ as uraninite towards the bottom of the Pourbaix diagram, this yellow color shows that it's insoluble. This is where we have solid phases. So we would like to keep our actinides in their insoluble, reduced state if we can in the geological disposal facility. So having your actinides in your mineral as a tetravalent oxidation state is a good thing. As you start to oxidize, they start to become more soluble. So we understand that these minerals, tend to have uranium in the tetravalent oxidation state, or are they in the tetravalent oxidation state? And that's something that we really started to probe when we started to synthesize a lot of these minerals, fabricate them synthetically. We found that actually they're not all uranium-4. So we wanted to go and investigate this on some natural specimens. And the way to do this is using a technique called X-ray absorption spectroscopy. For those of you who are not familiar with this, the very basic concept is we have an absorbing element. In this case, the talk I'm going to give today is around uranium. So an X-ray is a particular energy is fired at that absorbing atom, a particular energy. It then emits a photoelectron. The photoelectron interacts with the neighboring atoms and creates an interference pattern of reflective photoelectron waves. They interfere, and we're able to build a spectrum a little bit like this one at the bottom, which gives us lots of information about that particular element's speciation and its coordination environment with the other elements surrounding it. So the Zanes region here gives us some information about oxidation state and electronic structure, whereas the XAFS region here gives us more information about the local atomic structure, things like bond distance, coordination number, and so on. So what I'll talk to you about today is data that has been gathered across a lot of different beamlines. It took us a long time to get to the technique that gave us the answer. And it's worth saying that when we started doing this work, the technique that gave us the answer hadn't been fully invented yet. So it's been something that has been developed over the course of the last, I guess 10 years or so. Most of the work, I want to just give kudos to this young lady here. This is Dr. Lucy Mottram, who was doing her PhD on this at the time. She spent a long time at a lot of synchrotrons, and it was very hard work, and she slept a lot at the beamline. So I have to give kudos to Lucy here. And I just want to talk a bit more specifically about the techniques, because it has been an evolution in our understanding on these minerals, and it's kind of evolved at the same time as understanding these different techniques that we've been using. So when we're trying to understand the speciation of uranium with X-ray absorption spectroscopy, most people tend to use the uranium L3 edge. What this diagram here is just showing the different energy levels that we're exciting in the spectroscopy experiments. And the uranium L3 edge here, we're looking at these these particular valence levels. And these are the spectra that you get. So in the blue, we've got uranium 4+ compounds. In the green here, we have the 5+, and these are all 6+ compounds. And just the thing I really want you to take away from this is you can't immediately see a lot of difference in the shapes and the positions of these 5+ relative to the 6+. So it's quite difficult to tell with uranium L3 edge, the speciation. You can tell 4+, that's kind of easy. You can sort of tell 6+, but you can't tell whether you've got a mixture of 4, 5, and 6. It's quite challenging. Things do improve when we start to plot the oxidation state as a function of the position of the white line. We can do this in 2 different ways. And we can see that things can cluster in a certain position around uranium 4+, uranium 5+, and uranium 6+, but there's still quite a lot of scatter in the uranium 5+. So what we ended up moving towards, and I'll show you data from all of this today, is another technique where we're probing the uranium M4 edge, but with a slightly different technique. Is called HERF-D, so high energy resolution fluorescence detection zones. And this is a slightly different spectroscopy configuration. It's more of an emission spectroscopy. But here we're probing a different energy level. And if you take anything away from this, it's this particular fact. I've plotted the same standards over here. And what you can see, first of all, this is really nice. In U409, which is a combination of uranium 4+ and uranium 5+, we can see we've got 2 distinct peaks. You can really easily distinguish the different oxidation states of uranium. And actually, when we go over here to uranium 6+, there's all sorts of really interesting structure that you can start to pull out from these spectra. And just comparing the tightness of the kind of statistics that we get on the uranium 4 and 5 in these different techniques, this just kind of highlights that we're actually getting a little bit of a better idea of the oxidation state of our minerals when we're using the M4 edge HERF-D zones technique. But this will hopefully become apparent as we go through the talk. Okay, so the mineral that we ended up putting a lot of effort into was this calciopyrochlore. Again, this was work by Lucy that we're just kind of preparing now. So we had this particular sample. This is the pyrochlore sample here. It comes from Parry Sound in the Canadian Shield. Really nicely, it was located right next to a whole bunch of zircons. We got some help from Catherine Mottram at the University of Portsmouth to do some uranium lead dating for us, and this put us around about 1 billion years old, which is consistent with other literature from and measurements from this area. Just some information here. You can see the distribution of uranium in the mineral. We have this main 222 reflection of the pyrochlore, so it's pretty much completely amorphous, but you can see there's a little bit of crystallinity still remaining, and also in the zircon. This is a uranium, a calcium-rich pyrochlore. It has niobium also on the B site. The full formula is given down here at the bottom. It's obviously quite complicated, but we'll just kind of keep it short for now. So we took this sample, and we took a bulk sample to start with, and all the spectroscopy I'll show you in the next few slides are bulk samples, and measured them with a couple of different techniques. So this is the uranium L3 edge zones, and we did some fitting against some standards of different uranium oxidation states. And what you can see here is it comes up as a mixture of uranium 4+, some 5+, and a little bit of 6+. Okay, so the assumption is that these minerals are always 4+ in nature. So here we've got a really strong indication that there's quite a bit of 5+ here and a tiny bit of 6. When we apply the HERF-D technique at the uranium L3 edge, we see a slightly different picture. This time we have no uranium 6+. It's a mixture of 4 and 5. When we do the uranium M4 edge HERF-D zones, this is the one that can pick out the difference between the 4, 5, and 6. This really clearly shows us that we do have a big contribution from uranium 5 and 4, and actually quite a large contribution from 6 as well. So these are all very contradictory results on the same sample. And if I put them all together into one table, we can see the different percentages of uranium 4, 5, and 6. So the 5 ranges from kind of 40% to 60%. We have one technique that's telling us we've got 35% of uranium 6+, and one that's telling us we've got none. These are all obviously fitting techniques where we've taken known standards and applied these to our data, and they've come up with slightly different results. The EXAFS analysis, which I'll show you on the next slide, also gave us an oxidation state of something that was closer to 5. So these are the estimated oxidation states, the mean average oxidation state across the sample. So we have something that's definitely more than uranium 4+, but not quite uranium 5+, depending on the technique that you use. Okay, this is really interesting because we we thought that these were only 4+. Just quick look at the EXAFS analysis on this. It's quite challenging because, as I showed you, these minerals are almost nearly metamixed, so understanding the long-range structure is a little bit challenging with the EXAFS fitting. But what we were able to do is to fit these EXAFS spectra with 3 uranium-oxygen paths, and 2 of these here are really representative of uranium 5+ in uranyl coordination. So this is again giving us further evidence that there's uranium 5+ in these minerals. We also have a uranium calcium, uranium niobium, which is consistent with the formula that we had from the electron microprobe analysis. So, I mean, all of this goes to show, this is what you Google, this is what you get when you Google cartoon of uranium 5+, you get a Pokemon. So, I mean, all this shows is that it kind of challenges some of the assumptions we have about the long-term stability of uranium 5 in nature. It's usually only thought to be a transitory species that, you know, it may exist for a matter of, you know, minutes. It's on its way to changing into uranium 6, usually an oxidation reaction from 4 to 6, that 5 might happen in the middle. But actually what we're seeing here is a uranium 5+ mineral that's been stable in nature for over a billion years, sorry, which is really quite remarkable and challenges what we thought we knew about uranium 5 in nature. And it's not that these minerals haven't been studied before, of course they have. It's that the techniques that we have available now are able to unpick some of the chemical structure in these interesting actinide and lanthanide types of elements. So the one thing that's always really bothered me about this, though, is the uranium 5 really in the mineral? Can we say for sure it's been there and it's been stable for a billion years? And okay, I think the concentration of uranium 5 we're getting from the spectroscopy measurements is quite high. It's, you know, on the order of 40 to 60%, depending on the technique. So it must be there in appreciable concentration in the mineral. But it's always bugged me that this mineral is very highly altered. You can see around the edge here that you've got some alteration. There's cracks through the middle. You can see even in the optical microscopy that it's yellow around the side, which is suggesting to us maybe that's uranyl, that's uranium 6+, and maybe it could be uranium 5+. So is the uranium 5+ signal we're actually measuring due to alteration and not because of it being inherently stable in the mineral? And actually, when we did the dating, what Catherine found was a second cluster around about 200 million years, which we think is associated with this hydrothermal alteration that we can see. So maybe the uranium 5+ that we see is actually associated with that, and it's only 200 million years ago, which is still really old compared to what we think, but not as old as a million years. So we investigated this a little bit further using some microfocus spectroscopy techniques. So here now we focus the X-ray beam down onto the specific sample that I showed you before. We can focus the beam down to 1 by 1 micron. This work was done at the Swiss Light Source, and by doing that we can get a range of different measurements. So we can map where the distribution of elements with micro XRF. We can understand something about the local structure with the micro XAFs, and if we have any crystallinity, we can do micro XRD, which we didn't in this case. So if we take a look at this same specimen, here we're focusing on the very edge of the altered region now. We can see a micro XRF map of the uranium alpha emission line intensity. So this is essentially concentration of uranium. And you can see that there's slightly less uranium at the edge, except for a couple of hot spots here. So this is indicating this is an altered region. And what Lucy did in her work was to take a series of XAS spectra across this transect to try and understand the uranium oxidation state. It's messy, right? So we're going here A to J out to the edge. And these estimated oxidation states were estimated using linear combination fitting against a series of standards. We did a lot of work. I'm not going to go into the details of how we did this because it's quite complicated, but this was the best fit that we could come up with. And then also the calibration line, where I showed you a linear regression of the white line position as a function of the oxidation states. And that gives you quite a large error bar. So if you squint and ignore the error bars, you can sort of think that maybe it's getting a bit more oxidized towards the outside, which would be consistent with the fact you've got slightly less uranium and it might be more oxidized on the edge. But this isn't really definitive enough for me. It's you know, it doesn't really give us the answer. Then we tried some spatially resolved uranium M4 hefty zones at the SRF, the Roble beamline. And remember, this is the technique where we can distinguish individual peaks for uranium 4+, 5+, and 6+. And these are just some of the standards to show you those peak positions. What we did was to make maps different energies representative of those different oxidation states. And the way that we do this is to take a different spectra to find the energy at which we have the maximum difference between uranium 4+ and 5+, and then between 5+ and 6+. And we make a series of maps at these three energies. So we end up then with a map that gives us a map of where all the uranium 4+ is. This is mostly all uranium 4+. The uranium 5 and 6 is slightly trickier because actually at this energy of uranium 5, you see how it also slices through the uranium 4+ and the 6+ spectra. So the maps that we're getting of uranium 5 are mostly uranium 5, but they're also exciting some of the uranium 4 and some of the uranium 6 as well. And with uranium 6, it's even worse. You can see that we're also transecting the uranium 5 and uranium 4. So our uranium 6 maps are kind of a mixture of 5 and 6. Okay, so we made maps and we used the maps to help us identify points to take spectra. I'm going to tell you that the spectra are more indicative in this particular case than the maps, but I'll show you another example in just a moment. The other thing to note about this is that this isn't micro focus. We call this spatially resolved or macro focus because here we don't have the same optics on the beam. We're able to slice a lot of the beam out to make it 300 microns in the horizontal and 50 microns in the vertical. And it also has this kind of oval shape, this kind of curve, which makes the images look a bit squished. So this isn't as highly focused as the images I showed you before, but it is still really useful for the features that we're looking at. So here's the area of our mineral that we image. This is the zircon that I showed you in the first image. This is kind of the mineral, and this is a line of cross-section that you'll see in just a second. So what we're looking at here, this is a map of uranium 4+. This gap that you can see, this lower uranium intensity here is relevant to this gap between these two minerals, just to kind of orient yourselves. And so this is showing us that actually we do have quite a lot of uranium 4+ in this mineral. The scale bar is just relative intensity of counts. So there is in these samples an appreciable concentration of uranium 4+ everywhere in the mineral, and that's consistent with what we saw in the bulk spectroscopy as well. Then we look at the uranium 5+, that is also everywhere. But remember, this 5+ map also gives us some 4+ and some 6+ as well. And the 6+ is lower in concentration. But remember, this is also a map of uranium 6+ and 5+. So it's difficult to distinguish exactly what's going on here. What we did do was take a series of spectra at these points. So the first one here is in the bulk. The second one here corresponds to this small island of slightly increased concentration of uranium 4+. And the third one is out on that altered rim and that very altered region. And just as a reminder, these are the standard spectra to show the difference between 4, 5, and 6. And I'm afraid Origin crashed on me when I made this graph, so it looks horrible compared to the others. But what you can see here is in the purple here, 0.1, so this is out here in the bulk, we can see that we have a concentration of uranium 4+ under this peak here, 5+ under this peak here, and no 6+. Okay, so this is like really confirming to me that the bulk contains uranium 5+. That made me really happy. When we go on to that point that has slightly more uranium 4+, we see that there's a slightly higher concentration of uranium 4+ here. Absolutely brilliant. So as well as having the 5, there's slightly more 4+. But then out here on the very edge of the sample where we have our altered region, there's next to no uranium 4+, a heck of a lot of 5+ and some 6+ too. So what this confirms is that what we're seeing in the altered region is actually been oxidized to uranium 6+, and it really helps to give some confirmation that these minerals really do contain 5+. So kind of put that all together and do the deconvolution of the spectra again. This time in the bulk, here we go. We've got about 60% of uranium 5+. That's consistent with these measurements. We have on the edge in the altered region mostly uranium 6+. So this kind of makes me really super happy. So the conclusions of that are that pentavalent uranium does comprise the majority of uranium in this natural pyrochlore specimen, and that pentavalent uranium can be really long-lived. You know, we're not talking about seconds or minutes here or a transitory species. We're talking about something that can be stable over very long geological time periods. And so if we think back to the context, maybe we need to worry less about the oxidation state of our actinides in disposal, because actually, you know, uranium 5 might be very stable over very long time periods. We may not have to worry about working really hard to design minerals that keep it in a uranium 4+ state, which, by the way, we have been doing for the last 20 years, working really hard to try and get rid of anything that might form uranium 5, and therefore plutonium 6. So perhaps we can change our minds there. And just kind of the last thing I want to say is this unique to pyrochlore? What about other titanate minerals that we find in nature? So we had a specimen of thorotite, which is this kind of brannerite structure here, so uranium thorium Ti2O6. And we took it to, this time, Brookhaven National Laboratory. We were doing some other experiments and we just chucked this one on at the end. Just had a quick look. We can see the uranium L-alpha spectra here. So we've got quite a lot of map. We've got a lot of uranium in there. And we took a few spectra just to kind of understand the general oxidation state. This is with uranium L3 edge again, okay? And so here's the thoratite. These are the different standards, uranium 4, 5, and 6. If we plot the E0 position as a function of the oxidation state, we see it's kind of oxidized, which is quite surprising. In this structure, we wouldn't really expect it to be up at uranium 6+, and there's some slight controversy in the literature about this based on a paper where someone did some Raman spectroscopy and interpreted a peak as uranium 6+, but it is probably more like it was a bad background subtraction. So we were a little bit surprised to see it up here, but thought, well, we need to investigate more. And so we took it to the SRF and did this mapping. And here we see really nice distinction. So this is uranium 4+ map. This is uranium 5+ map. And I really like this because where you've got lots of 5+, you've got no 4+, which really shows us there's some 5+ here. And the uranium 6+ map as well. And when we take spectra from these individual positions, so here is where we have a lot of 4, but no 5. Here is we have a lot of 5, but no 4. And here's our very hot spot of uranium 6. And when we do the deconvolution, what we find is that in this region, we have about 75% 4+ and 25% 5, so there's no 6. In this middle region, it's about 50-50, 4 and 5+. And in this region where it looks like from the map we have a lot of 6+, actually it's mostly 5+ because of that nuance that we had with the mapping. So is this uranium 5+ stable in nature, unique to pyrochlore? No, it's also in this thoratite mineral as well. So we're interested. We've got a whole bunch of other things that we've been looking at to try and understand, exactly what's the range of mineral species that you can have this stable in nature. So I will conclude on that point there and say that as we all know, titanate minerals are brilliant. They're my favorite type of mineral. They're excellent candidates for plutonium immobilization and disposal. And we're doing an awful lot of work to try and stretch our understanding of those. We think we have the first evidence for stable pentavalent uranium, not associated with redox reactions or anything like that, on timescales of a billion years. It's not unique to titanate pyrochlores. We see it in thoratite and probably lots of other minerals as well. The bottom line here is, we love doing this with uranium. It's really fascinating, but really for the engineering application that we're using, we'd really love to do this on plutonium-containing materials. Obviously, we're not going to find those in nature. We have to make those ourselves, which I can't do in my lab. So hopefully in the future, some people will be able to do that. So before I go, I just want to say thank you to an enormous group of people. This work has been performed quite over the last 10 years or so, and there have been a lot of people involved, in particularly the beamline scientists who have been really helpful, and the postdocs and the PhD students who contributed to the work. And thank you for your attention.
Wonderful. Any questions? Yeah.
Your stability of uranium 5.
Yes.
I'm a bit worried when I see that in the pyrochlore you have hydrogen. So it's very easy rapidly to change, to remove hydrogen and oxidize locally the uranium in a matter of hours.
So I guess my comeback to that, yeah, you're right. We've synthesized these same minerals in laboratory. So we spent a lot of time working with different starting precursors. So whether we use UO2, UO3, U3O8, we changed the synthesis conditions from a reducing one with hydrogen, nitrogen to argon inert and so on. And actually we're able to stabilize phases that have uranium as uranium 5+ that don't have hydrogen contained in them. So there is a sweet spot in this phase diagram where we can stabilize uranium 5+. And the question that we have now is, well, exactly how far does that sweet spot extend? So it's a good point. So maybe in these natural specimens, there may be some effect of that, but we can also synthesize them in the lab without the hydrogen. Does that help? Yeah. I've stunned you all. Oh no, Max is going to ask me a question. Be kind, Max.
Yeah, thanks a lot. Very interesting. I was just wondering if anyone ever tried to use the L1 edge.
Yes,
Do this.
yes. Oh, I haven't got this in the talk, but we did. I go back quite a long way. When I talked about these, so we've also done these with uranium L1 edge, and actually for concentrated samples, it works really very well. If you have very low concentrations of uranium, you know, there's not enough absorption. Essentially, you can't see it, but the uranium L1 edge actually gives you, on these calibration lines, it gives you a slightly tighter grouping than the uranium L3 edge. We also tried uranium L1 Herfty, and that was also really pretty. You get some really sharpening of the peaks, obviously, and you see a little bit more information. We didn't pursue that any further. I think there's probably a lot more information you can obtain about coordination environment using the Herfty at the L1 edge, and we didn't go any further, and we should, but we just haven't done that.
Okay, thanks.
Anybody else from the floor? Oh, yeah.
Hello. I have a question that how much concentration we normally put in these disposal mineral, like you said, titanite, because in natural sample the concentration is almost in part per million. In disposal we normally do the fraction of weight %. So when we increase these concentrations, there is local defects, and that defects make reaction zones. But you haven't talked about that reaction zone. Maybe maybe you have gone through some papers like these nanocrystals. Yeah, when we. But you didn't mention the resolution of the instrument, or what is the part size of that machine that, because I see in some picture that the concentration is in specific zones. So that zone will be highly defective. There will be atomic defects there, and that zone will be quite reactive. But you say that the oxidation is minimum at that stage in those figures. So how it's minimum, because the defect zones are quite highly reactive.
So I guess there's two things that I can say about that. So in terms of concentration in the ceramic materials that are intended to be made for plutonium, we're targeting kind of 0.2 to 0.3 formula units. So you know, it's quite a lot. And actually, you can see in the formula here, sorry, it's really small. We have it's about 0.3 more % of uranium in these minerals. So they're kind of comparable. In terms of defects, you have to remember, particularly in these natural ones, you know, they're completely metamixed almost. You can see there's no, you know, crystallinity here at all, a tiny amount of crystallinity. So defects are kind of like I don't know, a bit of an unusual concept in these radiation damaged materials, because there's next to no long range order at all. So it's all defect, I guess. So that answers part of your question. I'm not sure about the others, but I'd be happy to talk to you about it after.
I have one quick question. If the chemical conditions are driving oxidation to uranium-6, and with uranium, the oxidation clearly stops at uranium-5, is it the redox conditions, the thermodynamics were not appropriate for the production of uranium-6, or is it the crystal chemistry
I think, yeah,
stops the reaction and stabilizes uranium-5?
Yeah, that's a really good question. It's the crystal chemistry.
Wow.
For certain. Yeah, for certain. Because we synthesize these things in the lab. These are high temperature mineral phases. When we make them in the lab, they're, you know, 1250 degrees C. It has to be to do with the crystal chemistry. It just has to be that you can accommodate uranium-5+ really nicely on that A site of pyrochlore. It's just the right size. It wants to sit with the calcium. You need charge compensation to be able to fit it in. But if you've got the right elements as charge compensators to make sure that you know, everyone's living happily in that crystal lattice, then it looks like you get uranium-5+.
Brilliant. What a great testament to pursuing crystal chemistry and mineral science studies. And if anybody needed any encouragement to continue element mapping everything you touch,
Yes.
What a
Yes,
great,
that's
thank you.
good. Thank you.